Yeah.
Okay. So let's go. Let's start the recording. Let's start. Yes, you're there.
Yep.
Oh, actually, I have some corrections to make a little bit here in the in this thing about make files. I had a few little typos really. This is correct. GCC. This is how you compile. Minus I dot. The I means look for the header file in the following location. The dot means current location. And over here, um, again, in my make file, I can write the names of the files I wanted to include. And by writing this here, what happens is if I try to make this again and compile this again, if I haven't actually changed either of these files, it will know and it won't recompile. And that I achieve by writing these names of them here on the same line as the command. Also here, I have to write, these are not pre-built variables. These are variables I had to call them. I decided to call it CC, and then I can use it. So I can say $CC, which means like I'm writing GCC. And then if I want flags like minus I dot, I'll put them at the end. And then just the functions I'll put here. And then if I have many different examples of compiling a program, I have hello make, I have some other program, George, Michael, Fred, and then those are all different programs. They'll each one could use the same variable CC and the same flags, or not use the flags. But the point is, I defined it, and then if I want to change my compiler to, let's say, I don't like GCC anymore, I want G++, or I want some other compiler, I just change it once, and it changes for all of the examples that I have. That's the idea. Okay, so we did open. There definitely will be a question on the exam on how to do a makefile. Okay, so pipe, dupe 2 we talked about.
The last thing we finished out was pop open, key open, whatever.
We talked about waiting for the child.
Yeah.
There's also, I don't know if I mentioned, there's a wait PID. This is just regular wait. There's also a function called
for
wait.
A specific child.
Exactly, wait PID, and then there's a second parameter here, which is the PID of the child you're waiting for. We did XXL,
yeah.
XXV, system, popen. Okay. So popen essentially combines a whole lot of things. It creates a pipe and a fork and a child, and the child then writes to the pipe and the father reads to the pipe. So, and all that's done behind the scenes by using all those functions that we had before. It uses a special type called a file type. And look at this example. I do popen with this file pointer. Notice it's not a file descriptor. This is a type called file, and it's a file pointer. So I have a file pointer which points to what's returned by this popen. And the popen I did was do this command ls -l on a file called popen1.c and another file called temp.c, and I want it for reading, which means, wait a second, which means I plan to read from this pipe. So when I say do R here, I mean I intend to read. So now I check for an error. Remember, anytime I do a popen, it could fail. This popen could fail to create a pipe. So I check if there's some kind of I do if on this whole thing. If it's, what did I say? If it is null, then it failed. So if it's null, then print the ls command failed, exit. Else didn't fail. So now there's got to be something in the pipe. I did this command, it didn't fail, and I got something. I mean, actually, it could be blank. If there's That's an interesting question. What's called failing? Failing is like I had a typo. There's no, I didn't type the right command. But anyway, didn't fail. I read from PF. That's that same PF, that same pipe that I created over here, that file pointer, and read from it into the buffer called buff, which has the size buff size. In other words, don't read more than whatever buff size is, which is 200 in this case. So don't read more than 200, but read that and put it into buff and use the f get s. File get string. So it gets string, but the f in front means it works with a file pointer. And that's what I gave it, a file pointer. Notice read would not work here because I don't have a file handle. I have a file pointer. So I have to use f get s. Then whatever I did, then print whatever C++ is. What is C++? What is C? C is 1. So file 1 in the current directory is, and then I do C++, so it's going to go up actually by 1. So the next time I print something, it will be 2. And each time I print whatever I read. Now, what am I reading? I'm reading actually the output of the pipe, but am I reading the whole thing? I'm reading as long as see f get s also reads until a new line. It's another feature of f get s. In other words, it's not just going to read, just reads. It just reads and reads and reads and reads until it's end of file. But f get s reads and reads until an enter. So the ls, it gave me 2 lines because I gave it 2 programs to list, and each one had an enter at the end of it. So I'm actually just going to read the first line, and then I'm going to get a null. In other words, while it's not null, well, I'm going to read, no, sorry. While it's not null, it'll give me null when I get to the end of the file. But each time I read, I only read 1 line. So that's why I'm going to print file 1 in current directory is, and then whatever I got from the ls. File 2 in current directory is, and then whatever I got the second time. So I'm going to get, each time I do an f get s, I'm going to get 1 more line of the ls command. And then once there's no more lines, I'll get null. The loop will finish, and I do p close. P close works with p open, obviously. In other words, you don't just do close on it, you do p close. I'm finished with this pipe. The truth is, I don't really need to do it in this case because the program ends anyway. But if I would have more lines in the program, I don't want to keep these open pipes. I want to return them to their system resources. I want to give them back to the system. I don't want to bog down the system, right? If I would imagine I had a program running constantly in the background. So if I open up lots of pipes, eventually I'll run out of pipe. I won't be able to make any more. I have to close them. So that's p open, which you could be asked theoretically to write p open using, write a function that it does what p open does using execv and pipe and fork, and you could do it. Here's another example of where I say W, which means I plan to write to the pipe. So when I do this fprintf to the pipe, I'm writing to the pipe. Apples are tasty. Write means I want to be able to write to the pipe. So now I write to the pipe. And then that goes into the pipe, and it comes out of the pipe, and it goes to this command, sed. In other words, this is what the pipe has in it, essentially. So it's on the other side of the pipe. Think about it. In this case, this is what's on the, if I read an R here, then this is what's on the left side of the pipe. If I read a W here, then this is what's on the right side of the pipe. Right, R-I-G-H-T. So because I intend to write to it, so this is on the read side. And anyway, apples are tasty into the pipe, but what I get, and I printf, sorry, the pipe Since I'm writing into the pipe, I finished writing, this goes in, and this comes automatically out of the pipe. In other words, this fprintf didn't print apples are tasty. This fprintf printed it to the pipe. It went into the pipe. But since it was a write pipe, the pipe is now going to write to the standard out whatever this sed produced. And this sed produced the transformation of little a to capital A globally on this string. So I get the apples are tasty. All right, that is the end of this programming section slides. Now we have another topic. Signals. Signals is really part of programming. So, are you guys all there?
Yep. Yes.
Excellent. Okay, so kill is a command. It sounds like it kills something, but it doesn't. It just sends a signal to something. The reason why it's called kill is because a lot of times the signals that you send have the effect of killing something, of stopping a process. So the syntax is kill, and then the PID of whom I want to kill or who I want to send the signal to. So in this case, well, I don't have, this is just an example. So kill, which signals should I send? So here is a table that you can get by typing man7 signal. And it lists a bunch of signals. They're different on different systems, but they're more or less exactly the same. Maybe there's sometimes with one little difference. But these are the numbers. These are the defines, the names. So in other words, 8 is the number of the signal, and this define sig FPE is the signal, is equivalent to writing 8. And what does it mean? Core arithmetic expression. So can you guess what this means? SFPE? Sig
Exception.
Exactly, floating point exception. That's a floating point exception is 8. 9 is kill, to exit. And notice what it writes here. This is what it does. Exit, most of them do exit, which means exit the program. Core actually means it creates a core file and exits. A core file is a file that describes the memory, all the registers and what their values are at the moment of the error, so that I can check what error happened. So ignore means the opposite of exit. Just don't die. So for example, sig child, which is a signal that the child sends the parent when he's finished. That's how the wait works. If you think about it, the wait is waiting for that signal to come. Sig child means the child has finished. But I don't want to kill the parent just because the child finished. So I ignore that. That's the standard behavior. So the behavior of what happens when the signal occurs is listed in this table. If you have a broken pipe here, somehow somebody's writing to a pipe that was closed or something, that can cause you to exit. Okay. Different signals. These are signals are otherwise called interrupts. Okay, so let's go back. Kill system call can be used to send any signal to any process. If the PID is positive, the signal is sent to the PID, to the process with that ID. But if the PID, if the process ID equals 0, well, there's no process with that number. Well, maybe the system, maybe the actual operating system is process number 0. It depends. Sometimes it's process 0, sometimes it's process 1. But then the signal is sent to every, but you can't send a signal to the operating system, I guess, even if it is 0. So 0 is reserved for sending it. If PID is equal to 0, then sig is sent to every process in the process group of the current process. In other words, all my programs will get it, whatever the process group is. If the PID equals -1, and that's more interesting, then the signal is sent to every process except for the process. No, never mind. That's not that interesting. So here it says init, which is the operating system, is 1. Sometimes init is 0, sometimes it's 1. I guess it's anyway. This is what I wanted. This is the important note. If the signal number argument is 0, in other words, not the PID, but the sig here is 0. There's no 0 on the table. It starts with 1. So what would it mean to put 0 on the table? So then what happens is, well, the normal error checking is performed by kill, but no signal is sent. But this is a way to determine if a specific process exists. Because if we send a process the null signal, but the process doesn't exist, kill will return error -1. But if it does exist, it won't return -1, but it won't do anything to it. So sending the signal 0 is a way of checking if a process exists, is running. Because of the recycling of process IDs in UNIX, the PID may be in use by another processor. You cannot be 100% sure that the process you intend still exists. In other words, I could check, is process 7 around? And it says yes. Process 7 around? Yes. Then I check, is process 7 around? No. So then I know it's not around. But it could happen that I say, process 7, yes. Is it around? Yes. Then I check again. Is process 7 around? It says yes. But really what happened in the middle, process 7 died and a new process was created and it happened to get the number 7. So I'm not actually checking the same process. It tells me it still exists, but really the one I was looking for doesn't exist. So it's not 100% perfect, that system. So on success, 0 is returned, on error, and -1 is returned. So it's supposed to, if I send a signal and the signal reaches its destination, then I'll get a 0. But if I send to a non-existent, I can also send to either to a non-existent process, then I'll get a -1. The signal is pretty simple. 2 parameters, the process I want to send to and the signal I want to send it. Now, if I send it signal 9, which is kill, it'll kill the process. There's also a function called raise. And raise is equivalent to, look at this, kill, get PID, sig. So what does that mean? Kill, get PID means kill. Notice how you can do this in C and in C++, but they like to do it a lot in C. Inside the function call parameters, I do another function call. So it's as though I wrote the result of the function get PID. Well, get PID is going to give me get my PID. So if I'm process 7, it's going to return me 7. So raise is equivalent to writing kill 7 and then whatever signal I want. So what's that going to do? That's going to send a signal to myself. So that's what raise does. It sends a signal to myself. So I don't need to actually write it like this. I just write raise and then the signal I want to send. And raise means raise me, send me. What it would be funny if you would do like raise and then in parentheses 0. That would be funny because you'd be sending yourself a signal that does nothing except to check if you exist. Well, if I exist, then if I don't exist, then I couldn't have sent that signal. So it would be kind of funny thing to do. Now I just want to mention something really from operating systems, but the operating system maintains a queue for each process of the interrupts that have come to that process and have not yet been handled. In other words, it could be theoretically that a lot of signals come to me, signal 1, signal 2, signal 3, and I'm in the middle of tailing with the first signal. What the other signals might get put into a queue so that I'll deal with them when I'm finished this one. Because remember, a signal doesn't necessarily mean that I die. Could be after I deal with that signal, I'm ready to deal with the next signal. But so this queue could be a FIFO, which means first in, first out, like a regular queue. Ignore interrupts while handling interrupts or not. So here I ask a question: should you ignore interrupts when you're, in other words, let's say I'm handling one interrupt, in the middle I get another interrupt. In other words, I'm handling, I got a sig child signal, and I'm doing whatever that note tells me to do, which is not to die, but do whatever it does. And I'm doing that. I mean, it doesn't really do anything, but let's say it does something. I'm doing some long process, and then I get a sig kill, die. So what am I supposed to do? Am I supposed to die right now, or am I supposed to finish what I was doing and then take the next signal? Do I look in the queue? Is it really a FIFO, like, or is it like a priority queue? You know, or is it like, or is it the opposite of a FIFO, where the most recent one gets finished first? It's kind of like I'm in the middle of cooking an egg, and then the phone rings. So I go and answer the phone, and then the doorbell rings. So I go and answer the doorbell. So what do I do? Who do I finish first? Do I tell the guy at the door, wait for me? Tell the guy at the phone, wait for me, and finish cooking my egg? Do I say, no, it was an interrupt, so I answer the phone first and talk to the guy, wait to make the guy at the door wait? Or do I say, no, the guy at the door is the last one. He interrupted everything else I was doing. Finish with him, kind of like recursion. Finish with the door, then go back to the phone, and then go back to the egg. So is the last one that came the first one I finish? Or do I just ignore the ones that came until I finish what I'm doing? So I can ignore interrupts while I'm handling the current interrupt. So the process could decide. The default is to deal with the newest interrupt first, kind of like a stack. So that makes sense. In other words, I got interrupted on my interrupt, so I'm interrupted. So I have to stop. So I have to deal with the new one. So that means I'll have a whole queue of like interrupts that I have to get back to. So the UNIX operating system maintains an interrupt or signal table for each process. In this table is listed what action to perform when this is a different thing. This is just talking about the fact there's a queue. Just something you have to understand. Then a new topic, which is that there's a table of not of the queue, but of what to do when each signal comes. So we just saw that table. That table is this list here, essentially. But that table is the same for all processes. But the Unix operating system maintains a signal table for each process. So we have what action to perform when the given signal is received. Either the default handle will be called, in other words, either the table is the way it was originally, or a replacement handler will be called. Maybe I said, you know what, when signal such and such comes, don't do what it says in that table, do another function, do another action. Or the third possibility is I just ignore the signal. I could just say that signal, when the signal number 17 comes, ignore it. I don't care about that signal. Or the interrupt will be blocked, that is put in a queue to be serviced later. So ignore means I just throw it away. Blocked means I wait. I don't deal with it right now. I put it in the queue. This queue is usually only big enough for one interrupt. All further interrupts will be lost. So if the doorbell, after the doorbell rang, also somebody's shouting out the window for me to come, and then my child starts saying I need help. So I don't start going to all the other things. I continue with the guy at the door. Now, there's a limit to how many things, if I'm blocking, kind of. Here I'm blocking. I'm saying when the doorbell rings, I ignore it. But if the phone rings, then that will get lost because I only have one thing. If I'm blocking everything, then the phone rings, I put that in the queue, let's say, and then the doorbell rings, that'll be lost. I won't have a way to store that if I'm blocking. You can only have one blocked interrupt at any given moment. So here's the table. So our topic is going to be how to block and how to handle signals differently from the default. Like I just described that you could do. How do you do that? Just a second. So what do? We have something called a signal handler. I'm going to explain to you two different methods for how to do this. So the first one is with this command signal. It's very funny because you would think that signal sends a signal, but actually kill, we just saw, sends a signal. So what does signal do? Signal doesn't send a signal, it changes a signal. It changes the default behavior when a signal occurs. Signal installs a new signal handler for the given signal, which I specified by the sig number, the first parameter here. The signal handler is set to whatever is defined in the second parameter, which could be a user-defined function, or it could be the keyword that defines sig ignore or sig default. Sig default means set it to set it back to the default value. Sig ignore means when that signal comes, ignore it. I don't want to handle that signal. I want you to ignore that signal when it comes. So signal can do several different things, but we're going to focus on the other thing that it can do, which is that I set a handler here to tell it what I want it to do. Upon arrival of a signal with the number sig number, so what's going to happen is after I ran this function, when a signal comes with the number sig number, the following happens. If the corresponding handler is set to sig ignore, then the signal is ignored. And if the handler is set to default, then the default action is associated to the signal occurs. And if I gave it a handler, then it'll do the handle. If the handler is set to a function, sig handler, then the sig handler is called with the argument sig number. Important point. The signal sig kill and sig stop cannot be changed, cannot be caught, blocked, or ignored. In other words, I can't say ignore sig kill. Sig kill, I always want to leave, I have to leave open so that the operating system can kill a process if it wants. The signal function, using a signal handler function is called trapping or catching the signal. The signal function returns the previous value. The signal function returns the previous value of the signal handle. So it has a return value, which is either going to be an error or the previous value of the signal handler. In other words, if it's a define, then what define it would be. So here's a program to demonstrate catching or trapping of a signal floating point exception. So look what I do here. First thing is I write a function. This is a regular function. Void static means, well, so what does static mean? It means that the variable, what does it mean, static? In this context, as a return type. Oh, I don't remember exactly what that means. It means that it doesn't change. It means the first time it gets a value, but the second time it doesn't change. But okay, I don't know why what that means exactly for return value. And it, yeah. Okay. Think of something. Okay. So here's a function. Sig floating point exception. That's my name because that's just my name. I could have called it Michelangelo, but I called it Sig FPE. I could have called it anything. It's not a keyword or anything. It's not a special name. But I must write here exactly one integer parameter. I don't have to call it sig number. I call it sig no, which is sig number. But I could have called it anything, but it had to be exactly one parameter. You can't have more than one parameter. And then this is going to be my handler. A handler has to have a certain form. It has to return a static void. It has to be called some name that I make up. And it has to take exactly one parameter of type int. And then what do? I wrote u divided by 0, didn't you? And then I did send myself a signal called sig alarm, which effectively kills me. Sig alarm is one of the kill signals that kills me. So I kill myself. But first I type this. So now, so far I just wrote a function. I didn't use the function signal. Yeah, now I have to use the function signal. Now signal, remember, it maps the signal that I want with a function. So this is saying essentially that if sig FPE occurs, then run the function called sig underscore FPE. So then here I just check if it's an error. I just check if I get a sig error. If signal returned to me sig error, then it didn't succeed at doing this mapping. And I write can't catch signal. So fine. That's just to make sure I succeeded. But assuming that I succeeded, then I'll go on to this line. Y equals 7 divided by x. Notice that x is 0. So here I'm dividing by 0. That's illegal. So that will cause either what you call some people call it a hardware, some people call it a software exception. That will cause an exception. And will send the sig FPE signal to my process. U divided by a floating point. U divided by 0. That's a floating point exception. U divided by 0. So this hello should not get printed because the signal will get sent. It'll interrupt, and the normal behavior of a divide by 0 is to kill my program. But since I changed the normal behavior to be u divided by to print this, it's actually going to print u divided by 0, didn't you? So I actually improved my way of handling divide by 0 so that the program doesn't just end. It also first it prints out what happened. And then in order to actually end, I had to send myself the signal sig alarm. Or some other signal I could have chosen. If I would have erased that line sig alarm, then I would have actually come back and printed to print hello. So even though I divided by 0, the program would not end. It's only because I added this raised 0. But if I hadn't done this signal at all here, then also the program would have ended because the normal behavior of a divide by 0 error is to send a signal which kills the process. Okay. So here I did here I did another thing. So that was with the divide by 0. Here I do with a different signal. Now sig int, that's what I'm doing here. You see over here, signal, sig int. What is sig int? Sig int is a signal that I can actually generate from the keyboard. See, divide by 0, I couldn't generate from the keyboard. I created it in the code. But here I can create the sig int by doing Control C. Yeah.
It's something.
Let's see.
I can buy something. I want to buy.
Just a second, guys. Recording. All right, we're back to our recording. Where were we? We were, here was this divide. Let's do view, present. You divided by 0, didn't you? And we caught the signal. Didn't you see the point of my program is that normally if you divide by 0 in your program, the program will crash or end. But by writing it this way, I've now written a program that you can divide by 0 as much as you want, the program won't end. Well, actually it will because I did this raised signal. But if I would delete that line, then it would never end. And in fact, that's what I did over here. If a guy types Control C and sends the program the sig int command, so what's going to happen? So what I did is normally sig int Control C kills the program, but I did if I do first signal. I just say signal. First I check it. I always check it as an error with this if, but that's irrelevant. The main point that's relevant is the signal with sig in and sig interrupt. And what I'm saying is if sig int occurs, then do the function called sig interrupt. And sig interrupt is over here. So then if this just checks it as an error, if I don't succeed at my attempt to do that, and then I make an infinite loop. Now, an infinite loop, of course, is dangerous, but I do a special command pause. And pause is a command that means a system call also that says wait for a signal to occur. This is only needed so that the loop does not waste CPU time. In other words, if I would do just a loop with nothing in it, an infinite loop, then it would use up the CPU would like be running constantly doing that loop. And that was a waste of energy. So I do a pause here so that it loops and then immediately waits. But it'll keep waiting there. So it'll wait there. It won't loop again until I get the signal. So then what I do is I run this program and I hit Control C. And it'll print, it'll get Control C and it'll say, oh, well, SIGINT is defined to run this program. So it'll run this program and it'll write on the screen, received SIGINT, but I ain't quitting. And then it will return. In other words, it won't end. It'll go back to this pause. This pause already did its job. It'll be the loop, though, will cause the pause to occur again. And again, it'll wait. And again, no matter how many times I press Control C, the program will just say receive SIGINT, but ain't quitting. So that would be like a way of preventing SIGINT from actually killing the program. Now, wait a second. Didn't I say before that SIGINT can't be blocked?
I have a question.
Yeah, go ahead.
You go back to the slides with the code.
Wait, all right, just a second. Where is? Oh, sig stop. Okay, yeah. You want this one, yeah?
Yeah. So declaring the sig interrupt as static void makes it so that it sends a signal if you type a key. I'm a little confused.
No, the static void I didn't explain. Not important.
So So what is sending the signal exactly? Like I don't know. I don't see that in the code.
Oh, you don't see, right. In the previous example, what's sending the signal is the 7 divided by x. What's sending the signal here is something external that the user, when you run this program, holds the control button down and then presses the letter C. If I do that on the keyboard, that normally would kill the program. But in this case, it won't, because I've handled that signal in a different way than the default.
So, okay, so where in main is sig interrupt being called?
Nowhere. It's an interrupt. The main is just sitting there doing nothing. But then when the user holds the control button down and presses the letter C, a signal gets sent by the operating system to the program that is running, indicating that it should die because it got a SIGINT. But my program won't die.
Right, but when you press Control C, that somehow calls sig interrupt, right? Because you're printing received SIGINT, but I ain't quitting, right?
Yeah.
So Control C, how does Control C call that function?
Because on the first line of the program, I said signal, and then I wrote SIGINT, sig interrupt, which means signal means rewrite the signal table such that SIGINT is no longer defined as it was in the signal table. Remember, SIGINT is defined over here. Where is it? Here, the second one, number 2. It's defined as exit. It's supposed to exit the program. I'm rewriting that and saying, no, don't do that behavior. Do this behavior, print receive. That's all you're supposed to do.
Okay, so what you wrote there is kind of redirecting into the code that you wrote for sig interrupt and printing out sig but I included.
Exactly. In other words, I have to do the two together. I have to first define a function that has a certain structure, has to take an int, has to have be void, static, and then I can write whatever I want inside of it. I have to write that. Once I wrote that function, I can then connect that function. Notice this sig int is a pointer, is essentially a function pointer. It's pointing to that function. And I'm saying connect the interrupt sigint with that function. When sigint occurs, you'll run that function that I defined. Is that clear?
Yeah, and what does pause do? You may have explained it, I might have been spacing out.
Pause says wait for a signal to occur.
Okay,
Any
fine.
signal. It's not technically necessary in this program. I could have written if I wouldn't have written a loop at all, I mean, I had to do something. I could have written like, cin, so just wait. Right, I could have done that. But I used pause. I needed it to wait so that I'd have time to press Control C. Okay, so now another example. So we saw, wait a second. So we saw two different ways to send a signal. One is that the program itself does something like dividing by 0, which causes the signal to occur. Second is here by Control C, the user types Control C and sends the signal. Either way, from the perspective of the sig interrupts table, it's the same. Either way, a signal occurred. And the third possibility is that the program itself sends a signal, which I don't actually do here. But let's look at this anyway. It's missing something here. This is funny. Yeah, I think I should add something to this program. So well, let's see what I do. It's funny that I did it this way. If I wrote a function here, forget about this function. I wrote a function here, and then I say like this. If I do signal, and I say connect the signal called sig user1. By the way, there is a signal called sig user1, of course. Otherwise, that wouldn't make any sense. Over here, you see sig user1, sig user2, and 16 and 17. So what I'm saying over here is connect sig user1 to this program, sig user, and connect sig user2 to that same function. Now, I'm allowed to do that. I'm allowed to use the same function for several signals. No problem with that. But then what do I do? Okay, and then I do a loop. And I'm in a loop, and I do a pause. And I'm just sitting there. Oh, I know I did. It's fine. I'm sitting there in a pause. Now, I'm waiting for a signal. So if somebody sends me the sig user1, I will go to this function. Now, in this function, notice that I got an int over here as a parameter, sig number. Well, that sig number, kishmo kenhud, its name tells me what it is. It is the sig number that occurred. So if it's sig, if this program over here, the main got a signal of sig user1, then that number will be 16. And I say if sig number 16 equals sig user1, well, sig user1 is 16, then print receive sig user1. Else, if it's 17, if sig number that I got over here is actually sig user2, it's 17, then print receive sig user2. So I'm just demonstrating that I can use this variable here to determine which signal I got. Of course, it only makes sense if I can get to this function by two different methods, but by two different ways, either by sig user1 and sig user2. Now, what I didn't do in the program is actually send the sig user1 or sig user2. I could do that by the kill command or the raise command. I could do raise sig user1, and then I would send myself the sig user1. But the way intended to do it in this program is a fourth way, which is you can write on the command line if you know the PID of this program, the process ID. I can write kill, here I'll show you. Stop share. Share. Here, so I can type, let's say I do, PS, and I see that WC is running in the background, and it's got PID 84. So I can do kill minus 16. 16 is sig user 1 to process number 84. Oh, it didn't die. Why did it die? Maybe let's do, if I do 9, it'll die. I bet. Yeah, it died. See, it says killed. It always tells me the most recent one that got killed. If I do again, PS, it doesn't tell me anymore about that. Just the first time tells me. So 9 killed it. 16 didn't kill it, although 16 also should have killed it, but I guess it didn't. I don't know why it didn't, but if you look at the table, it's actually slightly different. 16 is like terminate, and the other is exit. I don't know. They're slightly different, but imagine normal. In many cases, it would kill it. Maybe something special about PS. We have another. Anyway, so about WC. So I can send a signal like that. That's the intent. The intent of that program is that I run the program and then I do kill minus 16, and then the PID, whatever it is, 1122 of the process. Then the process will get signal 16, which is sig user 1. And it will do whatever it's defined to do when that signal comes in. So that's another way to send a signal. So we saw there are 4 ways. One is if the program itself, let's say, divides by 0, and then it'll send a signal. Another way is, what was the second way?
Control C.
I guess Control C. Right, Control C. The third way we didn't see, but I told you would be if in the program I used the kill command. Remember, the kill is also there's a command on the command line that we just saw that kills, but there's also a kill that's a C program, a C function.
You said the Control C is a kill function?
No, here. Did we see kill? Here, kill. See, just like I did on the command line kill, there's a kill function here. We saw that, where I can send to a particular PID, like myself, for example, any signal I want. I could do 16 over here. And then I would send myself. So one way is by Control C. One way is by doing a division, let's say by 0. Another way is by running the kill command and sending it to myself, which I could also do with the raise command, because raise always sends it to myself. And the fourth way is by, on the command line, writing kill and then the signal number and then the PID number. So those are all different ways I can send the signal, but this program was not interested in that. It's just interested in assuming that the signal comes somehow, one of those 4 ways. But what happens when it comes? So what happens when it comes is that I print out receive sig user 1. And that's all. I don't kill myself. Now there's a special thing, there's a special function called alarm. And I want to show you how it works. Process sleeps until the alarm signal is registered. So in other words, we can use an alarm to wake ourselves up from a sleeping state. It's like a timer. We can set a timer. And it's a little bit complicated the way I did it, but let's look how we do it. First of all, I do a function called sig alarm. My own function, I called it sig alarm. I could have called it Alpha Romeo. I called it sig alarm. And it does nothing. It just returns. I could have even nothing there. I could have open and close. It does nothing. It just returned to wake up the pause. Okay. That's sig alarm. Then I make a function called my sleep. And what I do is in this function, I say the sig alarm signal, if I receive it, then go and do this function called sig alarm, which this function actually does nothing. So basically, if sig alarm comes, don't die, because normally an alarm kills me. The normal behavior for an alarm kills me. If I go back over here, do you see sig alarm? Yeah, sig alarm. See, it says exit. So that kills me, just like 9 kills me. Sig kill. By the way, what is 16? 16 is also exit. I don't understand why I didn't kill, but whatever. So sig alarm would normally kill me, would normally make me die, but what I did instead was to say return, do nothing. So there's no line in here that kills me, so it's going to do this function and not die. So that's what I do. I say, first of all, when the alarm occurs, do this function, which does nothing. Then I say, set an alarm for n seconds. What's n seconds? That's whatever value I got. If the person running this function called my sleep gives me 3, actually, it's not n seconds. I think it's nanosecond. No, I think it's n seconds. Yeah, I think it's number of seconds. So however many seconds he gives me, that's how long I'm going to sleep for. So I go to sleep. Actually, I set this alarm doesn't put me to sleep. This setting the alarm, what does it do? Can anybody tell me what it does? What do you think it does? You can guess.
Besides cheating and rating that it starts a timer.
Right. It does say start a timer. It's a sign of a dumb question. It starts a
Oh, where
timer. What
does
does
it
that mean?
next
What does
come
that mean?
from?
It starts a timer. Lamaisa, what does that mean? So let's say a timer for 5 seconds. What's going to happen in 5 seconds?
It'll
What's going to
send
happen until 5 seconds? And what's going to happen at 5 seconds? That's my 2 questions.
Is it running in the back? Is it just running some kind of timer function in the background that counts down and then it sends a signal or whatever they'll signal?
Well, so first of all, you answered the second question. What happens after 5 seconds? A signal gets sent to me that says alarm finished. Alarm, 5 seconds are over. That gets sent to me. Who sends it to me? The operating system. It's the operating system's job to send me that signal. I requested him to send me a signal in 5 seconds. So he will send me the signal. But do I go to sleep now? You said it's running in the background, so that's not right. I actually do the next line and the next line and the next line. I just keep going. I just send an alarm. It's like I'm running a race and I'm giving myself 5 seconds to run the race. And I do however many commands I want, I can get finished within the 5 seconds. And the minute 5 seconds is over, I'm going to die. So like if you want to do an infinite loop in your program, but you want it to end eventually, you could, like some kind of recursion or something. You want to just play around infinitely. You could make an infinite loop, but then put a timer, and then it'll stop after 2 seconds. So even though it's an infinite loop, and theoretically from a coding perspective, it will be infinite, an alarm will come and kill you. An external event, an interrupt, will interrupt you, will stop you in the middle of your loop. So I didn't, in this program, I didn't want to continue on. I didn't want to do anything, so I wrote the next line as a pause, which means stop in your tracks. But normally, he would just keep running. And theoretically, if the program got to the end, well, this is a function. The function getting to the end doesn't mean the program got to the end. But if the program got to an end, then the alarm would never occur. You know what I mean? There's no point in sending an alarm to a process that's already finished. But I did a pause here. So what's going to happen is the program is just going to do nothing until it gets any signal. Could be a control C, but it also could be the control alarm. So I'm essentially waiting here for the alarm to occur and doing nothing. Now the alarm occurs, and after 5 seconds, and I run and do this function over here, which is nothing. I don't die. And then I come back to this line, return, and then there's a special feature of the alarm function, which if you give it 0, which is kind of a weird thing to do, give an alarm 0, it tells you how much unslept time remains from the previous alarm. So in other words, if I run the program like this, print, go to sleep, and I say my sleep, I run 2. So I'm setting the alarm for 2, and then I'm doing a pause, and then I'm waiting. And after 2 seconds, sends a signal, it finishes and returns me the result of alarm 2. Unslept should probably be what value? What would you say the value of unslept should be here? Remember, unslept time is the amount of time that the alarm was set for 5 seconds, but I only waited for 4 seconds. So it'll be 1. It'll be how much time I didn't sleep that I was supposed to, or I called it unslept, but it's really unused time of timer. What should it be in a normal case? What would you think it would be if I just ran this program and did nothing else? Or put another way, make it easier for you. How could unslept not be 0? Shouldn't I wait here, pause for the 2 seconds, and then the alarm occurs, and then I return, and well, the alarm waited for its whole 2 seconds, so this will be 0. When would alarms unslept be not 0?
If you didn't pass a timer number, I don't know, with an error.
What? Say it again.
If it's an error, will it be 0?
No errors. I don't know why there should be an error. Assume there's no errors. What can I do from the command line?
You can kill it.
Or, well, killing it will kill it. Then nothing will happen. I kill the whole process, nothing will get printed, and this unset won't get printed at all. But what else could I do?
Alarm? Can you send the signal for alarm beforehand? Oh, can you just send any signal? Or some random signal?
Well, look at this program. Look what it does. I could send some other signal. Alarm I maybe also could send. But let's say I send some other signal that doesn't kill it. Like one of the signals that's ignore, like sig child. Now the pause will get that signal. And oh no, yeah, the pause will get that signal. I take it back. You stop to send the alarm signal. You send the alarm signal early. So I set the alarm for 5, but it finished after 4 because after 4 seconds I sent the alarm signal from the command line. So this pause will get it, and then it'll run here, do nothing, and run alarm of 0 before the time is up. Because I sent the signal early by the command line. So this will return me 1 second left. Okay, that's an example of any questions you can ask on that. That's alarm. Okay, an example demonstrating the sending of a signal to a child process. So child received sig user 1 by D. D is decimal. Get PID is give me the PID of myself. So I'm sort of saying I received the sig user and I am whatever get PID gives me. That is my sig user function. That's going to override the normal sig user function. Look what I do. If I define that sig user 1 should go to this function. This is the sig user 1 function. I called it sig user. I check for errors, blah, blah. Now I make a child. And if 0 equals child 1, which means it's child process, then print child is running and pause. Do a loop and wait, do nothing. I could also do some code. I could do whatever I want, but here I'm just doing nothing. I wrote some code because like the pause is really in place. So it's really in place of whatever the child is supposed to do. Else sleep. This is a race condition. In other words, I'm hoping that the child got to this pause before I start running the parent. So I did the sleep 4, but the truth is that's not a proper solution for a race condition because, you know, maybe it takes him more than 4 seconds to print child is running. In any case, I get here and I say, here's one of those examples of how to send a signal. I say, kill child 1. Now I'm the parent. I'm not sending this signal to myself. I'm sending it to the child process. And I know the child process's number because I created him. I, the parent, did the fork and got the child ID. So now I can use that child ID by saying kill, send signal to child 1. Which signal? Sig user. Sig user will, of course, is already overwritten and will say, we'll do this. We'll print child receives sig user 1. And it'll print his ID, the child's ID, which should be the same as whatever child 1 is. And then I send again another signal, which is kill the child, send him sig kill. Now sig kill I did not override. Sig kill is 9. That will actually kill the child. But the child will be what's called a zombie. Did we ever discuss zombies? Maybe in operating systems? No. The child will be a zombie. What does a zombie mean?
Yeah, we did discuss that.
When? In operating systems?
Yeah.
Yeah. So a child will be a zombie now because what's a zombie? A zombie is the undead. In other words, I killed him, so he's dead. But he's still hanging around so that the father can do a wait on him. That's what I do over here. I say wait. Remember, wait waits for a child. And I'm waiting for the child to die, but the child's already dead. Well, now he's dead. For a moment there, I killed him. For this moment, he was a zombie. Then I get to the next line and I waited for him. He's no longer a zombie. So I call harvest zombie child. Now he's actually not a zombie. And then I say kill child 1 with 0. Remember, 0 says, if he's no longer existing, tell me. So make sure the child process no longer exists. So I sent him the 0 signal, which doesn't kill him, but it returns me an error message if he's not around. And hopefully I'll get an error message because I did kill him. So there you see that the father can send a child a kill signal, and the child can receive it and print child receives signal. So this is a form of communication. Think about it, interrupts are a form of communication. The father can signal the child, and the child can read that message. That message is, I mean, I can't send him any information other than the signal itself. I can only send, the only thing I can send him is what signal am I sending you? In this case, 16. That's the only information you can get. But it's still, that's valuable. I can use that. In fact, SIG user 1 and SIG user 2 are designed and for the purpose of sending signals but user defines. That's why they're called SIG user. It's like I, the user, the programmer, can use them as opposed to the system. Important note. Yeah. You know what? I want to stop here. Oh no, when do we stop? We stop at 6:45 and then have a lab?
Yeah, but whatever since it's all one continuous thing with one.
Thank you. Truth is, this is the middle of a topic, so we really should go on. But when is the day over? At 7:30, right?
7:30.
I'm saying, but does it matter?
Nothing matters.
Well,
But
we don't want to go past 7:30.
We could go past 7:30.
No, we don't really want to go past 7:30.
Past 7:30.
No, I'm saying that how you divide the time doesn't matter because it's all the same people and all the same Zoom lessons. So I don't see why.
Yes, you're right. You're right. All right, let's go on a little bit more. Let's go on a little bit more, and then I want to have the lab. In the lab, I want you guys to work actually.
Yeah.
What should the operating system do if a process receives interrupt or signal X when it's in the middle of handling interrupt X? In other words, the doorbell rings and then another person comes to the door, and then another person. On some, there's the same interrupt, not a phone and then the door and then the door. On some operating systems, it ignores or blocks the interrupt until it has finished the first interrupt. In other words, I don't allow the same interrupt to interrupt an interrupt. If somebody came to the door after somebody else, so I deal with the first one at the door. If the phone rings when I'm at the door, I might go answer the phone. But if the door rings after the door rings, I make him wait. So on some operating systems, it ignores or blocks. What's the difference between ignore and block? Ignore means it goes away. I throw it away. Block means it hangs around. It waits. It waits its turn. Some versions of Linux do not do this. Instead, they immediately handle the second interrupt. But instead of doing the interrupt function handler, they do the default behavior of the interrupt, usually terminating the process. This can be a problem if your program is not properly synchronized. In other words, if I get some systems might, if another occurrence of the same signal occurs, they basically may just die. If I get two people at the door, I may just die. Because I handle the second occurrence, but the second occurrence I don't actually do according to your define, I do according to the default behavior. If the default behavior is not to die, then I won't die, but a lot of times it is. This leads to the desire to be able to block or mask interrupts during the handling of an interrupt. So in other words, well, for two reasons. First of all, if the phone rings when I'm doing handling the man at the door, I may decide that I don't want that to handle. Normally, I would go and answer the phone. I may say, no, I want to mask it. I want to ignore the phone when I'm handling the door. Or I may want to ignore another door call when I'm handling the door. So that's the concept of blocking and masking. Blocking means making it wait. Masking means ignoring it, throwing it away. So now I'm going to talk about signal that we just defined. We already used it now. and I want to talk about a certain feature of it that we didn't, or a certain behavior of it. That is the traditional behavior. And I call it traditional behavior because it used to be true. I don't think it's true anymore. But let's talk about it because it's relevant to talk about the old behavior because it's going to explain the existence of another function. So the traditional behavior of traditionally the signal function sets the handler only for the first occurrence of the signal. All subsequent occurrences of the signal revert to the default behavior. That's kind of weird. In other words, I define that instead of doing the normal behavior for my signal, do some other behavior. But that's only the first time the signal occurs. If the signal occurs a second time, go back to the default. It's only a one-time deal. So this signal that we've just been using all this time really traditionally only works for the first occurrence. If one wished to handle all following occurrences of the signal in the same way, one could redefine the signal again by calling signal in the handler itself. Do I have an example of that? No. In other words, what I mean is, in the signal itself, let's say this sig user over here, you see where I'm pointing, yeah? This sig user over here is the definition, is what happens when sig user 1 occurs. But now if sig user 1 occurs again, I didn't do that here, but if I were to kill again sig user 1, it might not run this function. Because like I said, traditionally it wouldn't run this function. How could I make it run it anyway? If the next line after this printf, instead of being nothing, was another line that said signal sig user 1 sig user, just like I did over here, then in the signal handler, I define that for the next occurrence of that signal, also use this handler. So it's like, even though it's a one-time deal, every time I call it in that deal, in that time, I redefine it for the next time. It's kind of like how, not really like, but it's kind of like how the Congress said you have to move the embassy of Israel to Jerusalem. And every president, and it was like, every president, every year signed a deference. You could only do a 1-year deference. You couldn't defer it for more than a year. But each year he would sign a deference for 1 year. And that went on for 18 years, So it's only for 1 year that you can do it. But if you keep doing it every year, then you can keep, it's like renewing your book at the library. Every 2 weeks, you can renew it again. And then you renew it again and again and again. So you keep it forever. But you have to keep on renewing it. So it's the same thing here. It's only one time, but in the actual time that it happens, when it gets used up, I could redefine it for the next time. So that's one approach. Can anybody think of a problem with that approach? Why that approach is no good?
You might end up with a infinite loop if you get stuck and you just keep.
No, it won't be infinite loop. I'll redefine it, and then I'll go out. And then I'll go out back to the main. And if the signal occurs again.
We don't have control over which fork gets done first, right?
That's true.
So
yeah.
Wouldn't that matter if the up?
No, because it doesn't matter because the father here is sending the signal. The child is waiting. He's doing nothing. He sends the signal occurs, he prints this thing out, he redefines the signal for the next time, and then finishes, and then the father sends another signal and another signal. The father keeps doing that, and the child keeps going back to this pause. Should work. But it won't work. It will work. It will work most of the time. But a weird thing could happen. I mean, not in this program. In this program,
if it ends randomly in the middle.
Oh yeah, it could happen in this program. Because what would happen if I change this to sig user 1 over here? So he would send sig user 1. Listen to this. He would send sig user 1. He would come up here and start printing child received. Then there'd be a context switch before he finished printing. I'd go back to the father. And the father would run sig user, child 1 sig user again. He would then receive a second SIG user, but he was in the middle of this SIG user. He hadn't yet gotten to the next line where he's going to redefine what to do for the second SIG user. But the second SIG user came. In other words, the second SIG user came too early. It came before I had a chance to redefine it for next time. So then it would actually kill my program. So it wouldn't work if, depending on how quickly the father sent the second SIG user. Maybe that's what you meant, whoever spoke before. But the SIG user could get interrupted in the middle with another SIG user before it had a chance to redefine the SIG user. Therefore, it might make sense in some old Linux systems to ignore the second guy who comes. Remember I said, if two guys come to the door, don't let the second guy interrupt the first guy if the same signal comes. And you see the logic of it now? Since the same signal comes, well, I'll wait till I finish. And that means I'll wait till I actually redefine it for the next time. So when the next guy comes, it'll actually work. So that's why some versions of Linux handle the second interrupt, but some don't. On some operating systems, it ignores or blocks the interrupt until it has finished the first interrupt. And we see why. But on some it doesn't, so then that won't help. So what we want to do is actually ourselves block other signals from occurring, other signals from bothering us. So that's what I said. So we could call the handler itself, we could call signal in the handler itself and redefine what to do in the handler itself. A problem can arise. Here's what I just told you. If an interrupt occurs before the handler has time to reset itself as the handler, then this is a classic race condition. And I don't and now I don't know what's going to happen. Depends on the operating system, if it ignores it or if it actually handles it. SIG process. So we're going to attempt to solve this problem with SIG proc mask. Special function. But it's not really going to help us. But let's see if the idea. SIG proc mask is used to fetch and or change the signal mask of the calling function thread. The signal mask is the set of signals whose delivery is currently blocked for the caller. In other words, there's a set of signals which are blocked, which if they occur, I will temporarily ignore them. Remember, block does not mean ignore. Block means put them in the queue. Wait. So that list could have 0 elements in it or many signals in it. I can use this function to fetch or change the signal mask in the calling thread, in whatever thread I'm in, whatever process I'm in. So how do I use it? So here it takes how, which means like what to do, and then a set of signals, and another set of signals. This set of signals is what I want to change, what I want it to be, and there's the things I want to block. And the old set, are you guys hear me? Can you hear me?
Yeah.
Thanks. The old set is whatever it was before I did the change, in case I want to know. So in other words, this is what to do. This is the set of things to change. Sorry, this is the set of things to change, the set. And the old set is their condition before my change took effect, in case I want to keep track of it. So the behavior of the call is dependent on the value of how. So this is a kind of function that you would say is not following the principles of good design, because here you have a function that it's like a duck, it also swims, also flies, also walks. does everything.
Is it a nuclear duck?
It's a nuclear duck.
You know that BB speech from like 50,000
Yes.
years ago?
And I know you're talking about like the meme that they made about it.
I don't know about the meme. All I remember is watching him speak in the UN.
Oh, you don't know the meme? All right. You have
No.
now caused
Well,
me to.
I actually saw the speech, so I know there's another one with BB. Let me ask my Israeli people.
Yeah. Okay. So we are here. Oh no. That's something else. Here, we're here. So Sig Proc Mask. That was our musical interlude. So like I said, this is a duck. Why did I say the duck? Because you give it like, what do you want to do? And then the set that you want to do it to is like, you could have like a function that like, you give it all kinds of flags. It does all kinds of millions of different things, but I mean, it's not so bad. Either you can block or unblock or set a mask. So let's see how we use it. Obviously calling Sig. So wait, so Sig Proc Mask, we can say a certain set of signals we want to block. We can take a set and say block them. Now, or unblock them. Now we could say, well, let's just do that inside the handler. Inside the handler, let's block whatever we want to block. Well, we'll have the same race condition. Maybe another signal will come before we set up the block of the signal. So that's not going to help us either. It's a nice idea, but we'll have a race condition. So obviously calling Sig Proc Mask inside the handler will not solve our problem, as it will create a race condition. Maybe we'll get the signal before Sig Proc Mask actually got called. So what is the solution? The solution is to use another function called Sig Action, which basically does everything, but it does it all at once. It does it in a atomic fashion. So there won't be, nothing can happen in the middle. We do something in an atomic fashion, not a nuclear fashion, an atomic fashion, then it's one thing. So you can't interrupt one thing. One thing has to either happen or not happen. So we'll use this new function that by default keeps itself as, first of all, it has a few features. By default, it keeps itself as the handler until you reset it back to the original handler. So we're going to, when we define our signal, we're not going to use signal at all. We're going to use Sig Action. And that will have a quality of being permanent. Thus, but I can unset it if I want. Thus, there is no need to redefine the signal handler in the handler code itself. And this function will also mask the same interrupt during the handle. It'll also it'll also have the behavior that if the same guy comes, if another guy comes to the door when I'm at the door, he will be masked. He will be ignored. And we can even add more signals that we want to mask during the signal handle. I could theoretically mask a whole lot of signals when I'm handling the signal, whatever I want to define. Obviously, this function is going to have a lot more parameters because it does a lot of things. I can choose what I want to mask. I can also choose whether it will be permanent or only one time. Now I wrote as a note, nowadays signal has been rewritten to essentially be a call to Sig Action. So that signal will now also remain set for future interrupts because signal no longer behaves the way it traditionally behaved. It now uses Sig Action. So example using Sig Action. Here is an example showing the use of Sig Action to set a new handler for the SIGINT function. Note the use of the Sig Action structure. Yes, it is the same name as the function. It's kind of confusing. There's a function called Sig Action and there's a structure called Sig Action. In C, so here's the, you know what? Let's stop for today on this and let's go to the lab because time's up. Stop share.
There's the famous song with BB and Net